Though it's already dinner time. Thanks for having you to stay for my presentation. Today I'm going to talk about the deep learning, how to tackle the traffic problem system, and spatial-temporal graph convolutional networks. This work was accomplished by my colleague Yu Bing and my supervisor Zhu Zhanxin. And luckily this work was recently has been accepted by the 27th International Joint Conference on Artificial Intelligence. And I'm very honored to share with you in advance. And I'm going to introduce my topic in 5 parts and leave about 3 to 5 minutes to answer the questions. Sorry. So why shall we study about prediction problem in traffic? As we know, in the big cities like the Beijing or the New York, there are massive vehicles and cause a lot of traffic problems, like the jams, accident, and parking, and also lots of traffic surveys we used, like the navigation systems and even the shuttle car surveys like Uber or Didi and even motorbikes rely on the accurate and timely predictions. And especially such as the speed prediction, the ETA, and traffic velocity prediction is very important for the government issues and for the private sector. And also, the predict problem in traffic is the key to the intelligent transport systems, which we are contributed to build our smart city nowadays. So there are lots of existing methods to study the speed prediction, basically on 2 methods. The first one is the dynamic modeling. The dynamic modeling uses the ordinary differential equation or PDE for modeling the dynamics of the traffic flow, or they use the systematic or the physical simulations to simulate the situation. The issue is that they may contain some impractical assumptions. Also, they require massive computational power, and sometimes the predictionary accuracy is not very satisfying. Therefore, people transport their focus on the data-driven method, since they can avoid unreasonable assumptions and explore the patterns and features directly from the data. So there are basically 2 methods. The first one is the classical machine learning methods, including the ARIMA, KN, spot vector machine, and the neural networks. But they contain some problems. They do not model the road problem very properly. So people use the popular approach, the deep learning, such as the deep belief networks, stack autoencoder, the recurrent neural networks, and the variation and combination of a purpose method to do the speed protection. But the issues over here is this: they only focus on the temporal axis, basically the time series, but not with the spatial one. So we want to formulate the speed prediction task under structured, motivated time series prediction. And we have m previous time steps. The purpose is to forecast the next h time steps. But the traditional method is to regard every node in a node of the graph and take them individually. But our formulation is that we want to model the problem directly on the graph structure, which is very natural and very efficient. So we want to put the special features extraction from a node network into the prediction process. So we give the road network a graph representation. It contains 3 key elements. The first one is the vertex. We use the monitor station, which will record the history records from the road as the verticals, and the connection between the stations at the edges. The last one, we use the weighted adjusted geometry as the weights. So we have a graph structured traffic data. So the problem is very natural to given previous historical records and the graph structure, and we need to give the best next h assumptions or the predicts. But the shame is that we are all very familiar about the classical convolutional neural network on the grids. But it's very difficult to do that on the graph since they are different structure. The grid, such as images or voice or text, they are very applicable to the classical convolutional network. But this is the problem of how to generalize the convolution from the regular grid to the graph. So there are basically 2 major approach to tackle this problem. The first one is called a spatial approach. First, we have a target node from a graph and to select the neighborhood. Next, we use a graph nomination to generalize the subgraph. And we can, from the receptive field, to get an ordered node in sequence. So they can apply one-dimensional convolution directly on the vector. It's just to transform the graph problem to the normal grid. The second one is called the spatial method. The spatial method uses the spatial graph theory. It transforms the problem to the Fourier domain. Actually, they use the fast localized spatial filters. It's like the kernels in the ordinary graph convolution, and they will use this to get the subgraph. Use this to do the convolution, and use graph crossing to do the subgraph or polling to reduce the complexity. So we define the graph convolution operator based on the spatial method. The graph convolution operator star G can be defined by the multiplication of the signal x from network with a kernel theta in the Fourier domain as follows. The first, we need to calculate the Laplacian from the weight matrix. It's very normal in the graph study. And we get the Fourier bias, the U, and the lambda is the diagonal matrix of the eigenvector of the graph. Basically, it's as the equation 2. So by the above formulation, a graph signal x is filtered by kernel theta with multiplication between the theta and the graph Fourier transform U transpose x. This is the overview of our proposed spatial-temporal graph convolution networks. The left part basically consists of two major parts. The first one is called the spatial-temporal convolutional block. The inner construction is in the middle part, and we have output layer to transform the inter variables to the final prediction we had. So we already talked about the graph convolution, but we do not know how to calculate the graph convolution. The previous method had to calculate this operation cost about O of n squared. So it's not ideal or practical to put it into practice. So we have two basic methods to do the approximation. The first one called the Chebyshev polynomial approximation. To localize the filter and to reduce the number of parameters, the kernel can be restricted to the polynomial of the theta, as equation 3 shows. But the TK used to be traditionally to use the Chebyshev polynomial to approximate. So we can get the graph convolution written as equation 4. And it's a very simple way. And the complexity of this graph convolution can be reduced to O of k times the number of the edge in the graph. And another one is that we can further simplify the calculation. We know the Chebyshev polynomial is a recursive definition. We just took the first two items to calculate this and can achieve more efficiently and faster calculation. And due to the scaling and normalization in the neural networks, and we can sum the lambda max, the largest eigenvalue of the graph, to 2, and we can just calculate the equation 4 from 5 at this way, and we can further simplify that by letting the theta replace the theta 0 and the theta 1, which is the parameters of the kernel, and also we can renormalize the W and D separately, and this will achieve some kind of computations stability. And we get the number 6. This is linear complexity definition. So after talking about the spatial one, we need to focus on the temporal one. And as I referred in the beginning, most of the ways are focusing on the time series, and they use recurrent neural networks, very famous, the LSTM, the GRU. But why not we use in this topic? The problem is that the online models usually have very time-consuming iterations. Also, they have complex gate maximum, makes it not easy to train. and also they are very slow response to the dynamic changes. So we proposed a new way, a convolution on time axis to capture the dynamics of the time series. So the input of the temporal convolution of each node in the graph can be regarded as m long sequence as y, and we use graph convolution kernel gamma is designed to map the input y to a single output element p and q. P and q is split in half, and we used a nonlinear sigmoid function this to control the output of the p and to build a residual connection to control the output of the p, also to capture the dynamics of the traffic flow. So the basic structure of the temporal convolutional layer is as the Fig 5 shows. Have the two convolution and the output of P and Q goes through the GRU and to get it up. And finally, we proposed a special temporal convolution block, as I referred to in the general overview. And we want to jointly precise the graph structure time to fuse the spatial and temporal features. So we designed a nickname sandwich structure. Why we call this? Because during the process between the temporal and the spatial convolution, we do the downsampling at first, the channel from 64 to the 16, and then upsampling to the back. This is a bottleneck strategy, and we can achieve the feature squeezing and reduce the parameters, and also we can achieve better representation of the network. So the input and output of the block is also 3D tensors, and the output, each layer can calculate first pass through the temporal convolution, then the graph convolution, and pass through a ReLU activation function, then the temporal convolution again. So the loss function is very natural to give is we use the mean square error to calculate, to measure the performance of our model. I will talk about the experiment and results in this section. Basically, we use the two data set. The first one is the Beijing East Ring number 4 rows, and the second is from California. The two data sets are about 2 months time, and we accept the weekends. The first one contains about 12 rows to prove that basically our method is functional. The second one contains about 228 and 1026 stations to do the prediction problem. And the area of the California, the data set shows as the Fig 7. And we aggregate our data in 5 minutes using 6 minutes history records, 12 data points to predict 50 minutes, 30 minutes, and 40 minutes traffic speed of the network. Also, we use linear interpretation to fill the missing data using z-score normalization to process the input, and we generated the weight accuracy matrix W through a sigma distribution to control the sparsity and distribution of the W, and the heat map of this is shown in Figure 8. Finally, we use the mean absolute error, mean absolute percentage error, and the root mean squared error to evaluate our model. This is the speed prediction speed plots in the morning peak and the evening rush hours. The red and yellow line is our method, and the blue line is the ground truth. Our major target is the GCGRU, which is the green dashed line. It can easily to find out that our methods is very efficiently capturing the dynamics of rapid changing traffic flows, also respond very quickly to the unseen circumstance. But the online-based model like GCGRU or FCRITM tend to pick on the histories, so it's an issue. Also, the time series and the classical methods suffered from memorization. And our method achieved state-of-the-art on all 3 datasets. This is a comparison of time consumption of training on the dataset PMD7. the left is a small data set containing about 200 points. Left is a large one, containing about 1,000 points. You can see that our method achieved like 14 times acceleration compared to RNN-based model, and still in the large dataset we achieved about 10 times acceleration. And the Fig 11 shows the test MSE and MAE during the training. And you can show that our method achieved a faster converge and more lower error accumulation. In summary, we proposed a general framework, the spatial-temporal graph convolutional neural network. It is the first time the pure convolution structures of the deep learning networks are applied into the traffic prediction. And also the sandwich structure we proposed achieved the scale compression and fit squeezing through the channel attenuation of the bottleneck structure. And the fast training and time saving, we achieved the 14 times acceleration of training speed on the medium data set. We also achieved over 10 times on over 1,000 nodes data set. We used the fewer parameters. Compared to GCGIO, we just need around like 2/3 the parameters, and we think the over 95% parameters than FCRSTM. About the scalability and flexibility, our network can automatically adopt it to the multi-scale node network. If it's a small one, contains several rows, or the medium one contains 100 rows, or the large one contains 1,000 rows, and with the reasonable costs. But for the RNN-based models, the consumption explodes when we want to test them on the large datasets. So that's the end. Thank you, and I'm ready for your questions.
Okay. Any questions about in-store? Okay, though you're my students, I'm kind of familiar with this work, but I still have maybe just one major question about this. Have you checked the results? I mean, especially on the convolutional kernel you applied in your graphic convolution operation. So after you training the data, so could you tell something? Maybe tell us something about this. I mean, okay, what about the traffic? I mean, the nodes, different traffic nodes has some certain relationship between kind of a traffic jam or something like what's the cost between, for example, this is the node 1 has very slow speed, but maybe half an hour node B has some very slow. Yeah.
Basically, as far as my understanding is asking what's the intuition of apply the graph convolution into capture the special features from the network, whether it's good or not, or even effective to apply this. We do some application experiments. We get rid of the special convolution and apply the same experiment on the data side. It turned out that the convolution do contribute to help the network to learn the information from the neighborhood and to get more accurate to the prediction results. As for how to represent or how we can show to people how the graph convolution contributes to it, I think we do not to analyze we have the deep inside of this, but our previous study also shows some statistical analysis about this approach they used to analyze this distribution and also to test the input and output from the graph convolution. But we think it's kind of very tricky to tell whether it's work or not, or even evaluate to this problem. Okay.
Okay. See. Okay. If there's no other questions, just thank the speaker again. So welcome to